Hi everyone, welcome to this new lecture of hydraulic machines. In this lecture, we'll discuss a concept of operating characteristics curve of centrifugal pump. So in the last lecture, we have discussed about the characteristics curve of centrifugal pump. And in that, we have discussed that it is of three categories, three types are there. The first category is, we have discussed about the main characteristics curve. The first one is main characteristics curve of centrifugal pump. And the second type is operating characteristics curves. The second one is operating characteristics curve of centrifugal pump. And the third one is constant efficiency curve. The third one is constant efficiency curve. So in the last lecture already we have discussed about this, the first one. So in that we have discussed about that the main characteristics curve, it is plotted by conducting a number of experiments on the centrifugal pump and by considering different parameters. So in the parameters, actually the graph was compared like speed versus of different parameters like head and discharge and power. So in that we have taken diameter as a constant here. So along with the diameter, like suppose when you compare this speed versus head, there you need to take power discharge is the constant, and when you compare the speed versus discharge, then there we have taken the h is the constant, and when you compare that speed versus power, then h and q we have taken constant along with the diameter. But here we are going to discuss about the operating characteristics curves. So in the operating characteristics curves, if you see that this diagram what you are seeing in this screen, so this indicates the relation between the discharge and the other parameters. So operating characteristics curves. So here the relation between, like the graph is going to plot between discharge versus the other parameters. Again, in the other parameters, what we need to consider? Head and power and efficiency here. And in this condition, we need to consider the speed and diameter of the impeller. Both are constant. Okay, speed and diameter. Here also diameter constant, along with the different parameters it is constant. But here for all these conditions, the speed of the turbine, speed of the pump and diameter of the impeller, okay, that is constant here. So let's discuss it one by one. So first one, in the operating characteristics curve, as I told you, that in the x-axis we are having discharge. So discharge unit we can write, this is meter cube per second, and in the y-axis we have meter. This is like head, that is unit is meter, and power, this is watt, and this is unitless efficiency. So all these four plots or four graphs what you are seeing here, these four curves are there. First curve, suppose let head curve is there. That means the relation between the head and the discharge. Second one is the input power, how much power you are supplying. Third one is the output power. This is our third one. This is second one. Second. This is third. And this is the fourth one, efficiency one. Okay. So this is the fourth curve. This is the first curve. So let's discuss one by one all this comparison between this head and the discharge, power versus discharge, efficiency versus discharge. So in this operating characteristic curve, first I'll consider the comparison or the relations between this head and discharge. So here in the graph we can write head versus discharge. This is the first one. So in the first you can see the head plot is started from here, like the head curve is started from a long distance from this discharge. So as I told you, this is our x-axis and this is the discharge value which is there. So this is our origin point. So 0 point this is. Then we can state 1, 2, 3, 4, 5, 6 like that. We can consider the value in the x-axis. Similarly, in the y-axis also we'll have different values will be there. For head it will be different value, for power it will be different value, for efficiency it will be different value. So suppose head is there. Then again suppose head, I'll take all, suppose 10 meter head, 20 meter head, then 30 meter head, then similarly 40 meter head, 50 meter head, 60 meter head. Okay, so different heads are there. So now if you see in this plot, we have the head is started a long, like a distance from the origin. That means if you see the discharge here 0, at discharge 0, you can see discharge is 0 here. What is the value of head? The head is maximum here. If you see the curve, it is indicated that the head is maximum here. Why? When the discharge is 0, that means at this position our delivery valve will be closed. Okay, that means at the pump we have two pipes are there. One is delivery pipe, another one is suction pipe. So here in the suction pipe we have a delivery valve will be connected, this one. So at this point, when we'll get the discharge 0, that means no water is supposed to come out from that pump, when delivery valve will be closed. Okay, so when it will be closed or when it will be completed, like suppose, let me tell you, this is, we are having the pump is there and the pump is connected, like it is kept in a reservoir or in a pond or in a lake or in some places from where the water supposed to be lifted. This is our suppose pump, and this, in this pump we have a impeller is there. In the impeller we have number of vanes are connected here. Okay, number of vanes are connected, and this is our delivery pipe. So this is the suction pipe and this is our delivery pipe, and this is the pump. This is actually sump. This is actually sump level or water level, we can say sump. And here delivery pipe is like up to this level we need to deliver the water or fluid. So here we'll have a valve will be there. So near to this we'll have a valve, and here also suction pipe will have a suction valve will be there. So water will be come from here and it will goes to this impeller. Then from this impeller the water will be existed from here. Then it will goes out. So this is our outer part casing will be there. So in the pump we have, like suppose if you can consider, this is our suppose impeller is there. Okay, this is our impeller, or you can say this is our, this part is impeller and this part we can write casing, outer part, and inside that we have a, this is our shaft, and the shaft will be connected to the motor. So this shaft will be connected to the motor. So by that the process will be like water will be started lifting from here, then it will be goes here. So now you can see, suppose our target is to reach the water up to this level. So that means that is our total head. So this is our total head of the water. Okay, so that is a maximum head. But here also same thing we are getting here, maximum head where you are getting when the water stopped flowing or when the water stopped discharging, there will be zero discharge. So discharge when you will do, when this delivery valve will be closed, then we'll get zero discharge. So discharge means already water is supplied to this one. So we reached a maximum head. So that's why when your discharge is zero, that means head, the maximum head is reached. Okay, HM also, that is called manometric head. Okay, so at next if you see in the plot, at discharge increases. Okay, the second one is when you see the discharge in increasing mode, then the liquid started flowing from the, like from the suction to delivery, like how it is flowing from the suction to, like it is coming to the impeller, then it's going through the casing, then it will go to this delivery pipe. That means when the discharge increases here, discharge value increases, that means what? The water is started flowing, the water started flowing, the water started flowing through the, you can say, impeller and casing. Okay, impeller and casing. So as you can, we have understood that here we already reached a maximum head when it is zero. So once it is increasing, that means you won't get more, like more value in that. Like you can ask also, it can be in increasing mode, why you only did decreasing mode? So, yeah, that is a good question. See, the head is nothing but up to what head, up to what height it is delivering. So if you see when the discharge is increasing, here head value won't increase here. Okay, because head is maximum here, we have, this is the maximum head. So when discharge is zero, we reached the maximum head. So when the discharge increasing, when the flow rate is increasing here, we'll have some limit value will be there. Okay, so and apart from that, some other reasons also there. I'll tell you that some losses will be there in the flow. We know that when the water is flowing or when the fluid is flowing through the pipe, we'll have some losses of, there are some losses of energy, we can say. So some losses will be there in the pump. So which kind of losses is there? And losses of hydraulic losses when it is running, when it is having the water is flowing through that. So hydraulic losses here, that is going to increase. Okay, and along with that also I can say that friction losses. So friction losses with respect to velocity, so that is there. Then apart from that also I can tell one more point. We know that when you are talking about the discharge, so if you are taking higher, suppose discharge is there, higher discharge in the sense our velocity also higher. If it is higher discharge in the sense our velocity should be higher. So higher velocity, at the higher velocity will have more losses will be there. So losses also high. That's why we'll get a decline curve here or decline plot here in this point. This is about the first category. The second category, what is that? The second point here, which one? This one, input power. So input power versus, let's discuss about input power versus discharge. So this also same thing, similar kind of things will be there, but slightly different because that is head, this is power. So here input power means, input power is nothing but, input power talks about, input power which talks about the shaft power, which the shaft power which is supplied by the motor. The shaft power which is supplied by motor. Already I told you previously, this impeller is, this is the impeller which is mounted on the shaft, and this shaft is connected to the motor, correct? So the power which is supplied by the motor to the shaft, and that is transferred to the impeller, that is nothing but shaft power, and that is our input power. Okay, so which is supplied by the motor. Now if you see this input power also, this curve also, like it is in increasing mode. Okay, how much discharge? See, more discharge, that means more mass flow rate. Okay, more discharge in the sense more mass flow rate is there, and more mass flow rate we require more power. Okay, that is one point. Second point, first question will be there, why it is not started from the origin? Again same thing, here also it is not started, here also it is not started from the origin. Why it is not started from the origin? The point is very simple. We have some losses will be there. Again I'm telling you, some mechanical losses will be there in this. Okay, some mechanical losses will be there. So to recover that losses, okay, even at the zero discharge, even at the Q equal to 0, if you see, we require at least minimum power, some minimum power required, okay, which will overcome the mechanical loss. Okay, now suppose zero discharge is there, that means pump is closed or pump is completed that work. So when you start the pump, at least initial level we need some power. While we have discussed on the cavitations and priming conditions, priming especially, initially we will supply some power to the motor, and that will be supplied to the shaft power, and that by that it is going to rotate. Even some initially will have some kind of losses will be there which is in the pump. To avoid that, to overcome that, to overcome that losses, we require at least minimum power to start the discharge. That's why the zero discharge also we require some amount of power, that one. Again, once it started, it will also continuously increase. Now even the head, if you increase, then our discharge also, like initially if you what you have seen, your head is increased at zero discharge, and when the discharge is continuously increasing, our head is decreased here. But here for the input power, I'll tell you one more formula. We know that power equal to rho g QH, rho g QH by 1000 in terms of what we have considered. So here only I can write P equal to, if I suppose only write rho g QH. Now here if you see this power also, this is constant value, this is constant, this is discharge, this is head. So head already we have discussed. Now here I can write this power is directly proportional to Q and directly proportional to H also. So here we can say H and Q already that is completed. Now power it directly is proportional to the Q. Discharge increasing, this input power also increasing. Okay. And as I talk about the losses, so even at the zero discharge, okay, the power is not zero. Already told here. Even at the zero discharge, some power required. The power will be not zero. Because if you see, even the discharge completed, our impeller is continuously rotating. The impeller will also be continuously at the ending condition. I'm talking. Starting condition I told you zero discharge also. That means when the pump started running condition, and when the pump already completed its discharge, that means discharge is zero. Okay, but there also if you see our impeller is still in the running condition. So there is some liquid will be there, and that will also in the running condition. So the input power, okay, so that will be continuously rises. Okay, that will continuously rises along with the discharge. Okay, that is the second point. I hope you understand. We'll go to the third one. The third one, what? That is the output power. The third one is nothing but that is output power versus our discharge. So this is also simple thing. So output power is nothing but here also the same equation I can write P out. So P out, that means how much output power you are getting from this. So here also we can write that rho g QH. Okay, this is we can write or not, but here we'll get the same thing. Like well, we can write the equation of this. Now if you see this equation, now we compare. Now this output power when we'll get, will start from the origin point. It is not like input power. Initially to start the pump, we require some minimum power to overcome the mechanical losses. But in the output means finally how much power you are getting from the pump. So the P output equal to these two constants are there. Now Q. So it will be directly proportional. It will be directly proportional to again Q. The discharge is there. So power increasing. Okay. The now see, this is the output power. Output power curve is this one. Okay, this is our output power, and it started from the origin. Discharge increased, power increased. Discharge increased, power increased. Discharge increased, power increased. So the output power increases continuously with respect to discharge. But here is there is a small concept is there. If you see the low discharge here low power. Okay, low discharge, low power. Similarly, medium discharge, here medium discharge is there, medium discharge, so medium power also will be generated. Okay, medium power will be generated. So up to a maximum power can be generated up to a limit. Up to a maximum, like up to a range, we have a maximum will get. Now when the discharge increased, when the discharge at high discharge is there, okay, so here write when we have high discharge. At the high discharge, we won't always get high power. So that means at this point, we won't get our maximum power. So here power will be decreased. High power, high discharge, our power will be decreased. Why? Because at the high discharge, sometimes the head drops look there. Okay, the head will be sometimes drop, and that will be you can say that yeah, when the liquid is flowing, like sir, when the liquid is flowing, see high discharge in the sense what discharge equal to, we know that area into velocity. So velocity is associated to this one. Now velocity, now when you are talking about high discharge, velocity also increasing. So when its velocity is increasing in this impeller, so when the impeller or the blade is running, so the velocity of water is very rare, okay, to the runner. So that means the velocity will be not directly contact with the blade directly. So there is some losses will be there actually. By that, we won't get maximum power. So that up to optimum limit, we can get maximum power with respect to discharge. So slowly again also it will be started decreasing because of the losses. Okay, yeah, the last one, The last one is efficiency. So now see, when you get this two powers, input power, output power, so finally what will get? Efficiency versus discharge. So efficiency, we know that formula. Efficiency formula what? That is output by input. So we got the output power, input power also we got. So from this, if you see, both are increasing, but at a certain level. Now in the efficiency curve also same thing is there. Up to a maximum level, up to a maximum point, it is increasing. Discharge increasing, efficiency also increasing. So at this point it is maximum. After that it started decreasing, decline. Here also the same thing will be there. At low discharge we will have the same issues. At low discharge we have, okay. So yeah, so when the fluid will be flows through the vein or through the blade, okay, we have like the involvement of water with respect to the vein or blade will be okay. So in that we'll get only some efficiency, so low efficiency will be there because it directly associated to the power. Okay, so see, both power are there, input power and output power. So output power more means will get efficiency more, but here input power more means will get less efficiency. When will get the less input power? When you can see that discharge is more, that means more power consumption is required. With respect to more power consumption, output power you are getting less. In that condition will get less efficiency. So low discharge will have low efficiency. As the discharge increases, as Q increases, you can say that flow aligns. The flow will be proper alignment with the impeller. Okay, the alignment of flow alignment with the impeller will be proper with the vanes. Then here also we'll see discharge increasing, our efficiency also increasing here. This is about the low. But when we'll go for high discharge, there it will be different. This is suppose high discharge is there, but here the efficiency is decreased here. So at this point we can say the loss of friction is more. Okay, the losses of energy we can say, or loss of friction, one more point we can write, the loss of friction is increasing. Okay, along with that also that recirculations is increasing continuous, like recirculations are there in the pump. Again, along with this also I can say that shock losses also will be there at the impeller output. Shock losses is available at the impeller outlet of the pump. So in these regions, due to these regions, the efficiency will have, like initially as per the discharge, efficiency also increase, but up to a certain limit. Okay, and after that it started decreasing. So I hope you understand this concept of operating characteristics of centrifugal pump. And still, if you are having any doubt on this and any query regarding this, you can give a comment on the comment box. Thank you all.